In this video, we will learn about universal logic gates. A logic gate which can implement any logic function is called as universal logic gates. Basic logic gates are AND gate, OR gate, and NOT gate. If output of AND gate and OR gate are inverted, that results in NAND gate and NOR gate respectively. Like basic logic gates, there is a logical relation between output and inputs in the case of NAND gate and NOR gates. For a NAND gate, the NAND operation can be explained as: if all inputs are at logic 1, then output is equal to logic 0, else output is equal to logic 1. For a NOR gate, the NOR operation can be defined as: if all inputs are at logic 0, then output is logic 1, else output is logic 0. This is the symbol of an n-input NAND gate and n-input NOR gate. There are n number of inputs and only one output. Now let us discuss two-input NAND gate. For a two-input NAND gate, the two inputs are A and B and Z is the output. So the logic relation between output and inputs are Z is equal to A NAND B. Z is equal to complement of A and B. The logic operation of this gate can be summarized as: if A and B is equal to 1, then Z is equal to 0, else 1. Or if A or B is equal to 0, then Z is equal to 1, else Z is equal to 0. This is the truth table of a two-input NAND gate. When both inputs are 1, output is equal to 0. If any one of the two inputs is equal to 0, then output is equal to 1. So if A is equal to B is equal to 0, Z is equal to 1. If A is equal to 0, B is equal to 1, Z is equal to 1. If A is equal to 1 and B is equal to 0, Z is equal to 1. And if both inputs are 1, then Z is equal to 0. So we can summarize the truth table of a NAND gate as: for a NAND gate, if all inputs are at logic 1, then output is logic 0, else output is logic 1. Now we will consider a two-input NOR gate. The two inputs are A and B and Z is the output. So the logic relation between output and inputs are Z is equal to A NOR B, or as an equation we can write Z is equal to complement of A or B. The logic operation of this gate can be summarized as: if A or B is equal to logic 1, then Z is equal to logic 0, else Z is equal to logic 1. In other words, we can define the logic operation as: if A and B is equal to logic 0, then Z is equal to logic 1, else Z is equal to logic 0. This is the truth table of a NOR gate. So we can summarize the truth table as: if both inputs are at logic 0, then output is equal to logic 1, else output is equal to logic 0. If A is equal to B is equal to 0, Z is equal to 1. If any one of the two inputs is equal to 1, Z is equal to 0. So the truth table of a NOR gate can be summarized as: for a NOR gate, if any one of the inputs is at logic 1, then output is logic 0, else output is logic 1. Now let us implement basic logic functions using NAND gate. Basic logic operations are NOT, AND, OR. Can be implemented using a NAND gate. So first of all, let us discuss the implementation of a NOT gate using NAND gate. So this is the truth table of a two-input NAND gate. If both inputs are same, then output is equal to complement of the inputs. So if both inputs of a NAND gate is at logic 1, then its output is logic 0. And if both inputs of a NAND gate is logic 0, then its output is logic 1. From this truth table, we can say that two inputs of a NAND gates are shorted, and if a logic value is applied to any one of the two inputs, then output is complement of the input. So this is the diagram where a NOT operation is implemented using a NAND gate. So if A is equal to 1, then Z is equal to 0. If A is equal to 0, then Z is equal to 1. Now let us discuss De Morgan's theorem. According to De Morgan's theorem, complement of A and B can be written as complement of A or complement of B. AB bar is equal to A bar plus B bar. So, NAND operation can be represented as OR operation, or a NAND gate can be used to realize an OR gate. So let us consider a truth table where there are two input variables. A and B are the two input variables. 0, 0, 0, 1, 1, 0 and 1, 1 are the four combinations. Look at the third column. Complement of A and B is 1, 1, 1, 0 for the input combinations 0, 0, 0, 1, 1, 0 and 1, 1 respectively. Now you look at the fourth column, complement of A or complement of B. So A is equal to 0, complement of A is equal to 1. B is equal to 0, complement of B is equal to 1. 1 or 1 is equal to 1. Similarly, for the other combinations also, we will get 1 and 1. Look at the last input combination 1, 1. When A is equal to 1 and B is equal to 1, complement of A is equal to 0, complement of B is equal to 0. So 0 or 0 is equal to 0. If you compare the third and fourth columns, we will find that these two are same. That means complement of A and B is same as complement of A or complement of B. Now let us implement an OR gate using NAND gates. So for a NAND gate, if A and B are the two inputs, then at the output we will get A bar plus B bar. So if the inputs A and B are complemented, then at the output we will get A plus B. A bar and B bar are the inputs for this NAND gate. So at the output we will get A double bar plus B double bar. So if input to the NAND gate is inverted, then output is A plus B or A or B. Now here that logic function is implemented. The NAND gates N1 and N2 inverts the input variables A and B. So output of NAND gate N1 is equal to A bar and output of NAND gate N2 is equal to B bar. And these two variables A bar and B bar are fed to the inputs of the third NAND gate N3. So output of the third NAND gate N3 is equal to A bar and B bar the whole bar, that is equal to A double bar or B double bar. That means the output of NAND gate N3 we will get the operation A or B. So this means that we can realize an OR operation using 3 NAND gates. Now let us discuss the implementation of an AND operation using NAND gates. Again, the number of input variables are 2. A and B are the two input variables. And 4 input combinations are 0, 0, 0, 1, 1, 0, 1, 1. Output of NAND gate for these 4 input combinations are 1, 1, 1, 0, and result of an AND operation is 0, 0, 0, 1. Comparing the third and fourth columns, we can say fourth column is the complement of third column and vice versa. That means if output of a NAND gate is inverted, we will get result of an AND operation. So here there are 2 NAND gates N1 and N2. Output of NAND gate N1 is equal to complement of A and B. So output of NAND gate N1 is fed to a second NAND gate whose both inputs are shorted. So output of second NAND gate is equal to A and B as second NAND gate N2 acts as an inverter. Now let us discuss the implementation of a NOT gate using NOR gate. The truth table of a 2-input NOR gate is shown. If you compare the input combinations, when both inputs are 0, output is equal to 1. When both inputs are 1, output is equal to 0. We are not interested in the second and third input combinations 0, 1 and 1, 0. From this truth table we can conclude that if same logic value is applied to the two inputs of a NOR gate, then output is equal to complement of the input. So here we have to short the two inputs of a NOR gate and a logic variable is applied. At the output of the NOR gate, we will get complemented value of the logic variable. So if A is equal to 1, then output of the NOR gate is equal to complement of 1 or 1, that is equal to 0. If A is equal to 0, output of the NOR gate is complement of 0 or 0, that is equal to 1. Now we are going to realize an AND operation using NOR gate. So for that, let us consider the De Morgan's theorem. According to De Morgan's theorem, complement of A or B is equal to complement of A and complement of B. So this means that we can represent an AND operation using NOR gate. Now proof of concept. Again we will consider a two variable truth table. A and B are the two variables. 0, 0, 0, 1, 1, 0 and 1, 1 are the four various input combinations. The third column of this table represents the complement of A or B or result of NOR operation. And the fourth column is the result of A bar and B bar. Comparing these two columns, we can say that complement of A or B is same as the result of the operation A bar and B bar. So now let us implement an AND gate using NOR gate. Output of this NOR gate N1 is equal to A plus B the whole bar, that is equal to A bar and B bar. So if inputs of the NOR gate N1 are inverted, then at the output we will get A and B. So A bar and B bar, the whole bar, is equal to A double bar and B double bar. This is the realization of an AND operation using three NOR gates. Now let us implement an OR gate using NOR gates. Compare the output of NOR operation and OR operation. We can say that third column is the complement of second column and vice versa. That means if output of a NOR gate is inverted, we will get result of the OR operation. So if output of a NOR gate is inverted, we can realize an OR gate. Two NOR gates are used to implement an OR operation, NOR gate N1 and NOR gate N2. Inputs to the NOR gate N1 are A and B. So output of NOR gate N1 is equal to complement of A or B, which is fed to a second NOR gate with both inputs shorted. So the second NOR gate behaves as a NOT gate. So at the output of second NOR gate, we will get A plus B. Thanks for watching Circuits Analytica. Enjoy learning. Please comment, share and subscribe our channel.